So thank you everybody for coming. I'm quite impressed this talk has gathered such a crowd on an afternoon after lunch of the last day. So I hope I won't be too boring with you. I understand you've just had lunch. Maybe I hope that you had coffee to keep yourselves awake. Like I said, I'm quite impressed the number of people who have showed up. I remember pitching this talk to a colleague of mine at Intel, and he's a kernel developer, Linux kernel developer, said, no, I'm not going to accept you. I don't want to see anything about C++. I even spoke to Linus once about C++, and I don't know if you've ever talked to Linus about C++. He's got quite an opinion about it. So some of the things I'm going to show are my phone. Just put it here. So nobody ever calls me. I never receive any text, and apparently this is the first time that happens. I was saying Linus has quite an opinion of C++. He considers many of the things I'm going to show as misfeatures. I consider them as features. So let me briefly introduce myself. I'm Tiago Macieira. That is me, working with high technology back in 1982. I've been involved with open source development for, well, over 15 years. I'm not going to say exactly how much. Most of that time has been actually working with C++. So if any of you were on my talk yesterday when I was talking about IPv6, I started my career in open source by working with IPv6. I was asked, what do you want to work on? I decided I want to make a browser capable of IPv6. And Mozilla at the time already had support for IPv6, so I started with the KDE's browser. And if you're familiar with KDE, you know it's written in C++. So that's how I actually ended up working with C++. Before then, I had submitted a patch to the Linux kernel. I had made a couple of modifications working with Pascal, with Clipper. But it wasn't until I started actually doing C++ that I got into my professional career. And both C++ and IPv6 actually landed my first job in open source when I went to work for Trolltech. And now I work for Intel as a consequence, as evolution of whatever I was doing back then. So, my job today is to say and convince you that C++ for embedded is possible and it's even a good idea. Let me just take a quick survey of the audience here. How many of you program for embedded systems? Okay, I should have asked the other way around, and since we're in Embedded Linux conference, that was to be expected. Quite dumb of me. How many of you do that with C++? You guys can leave. I will be reinforcing that idea to you, and hopefully I will be giving you more arguments whenever you come to a colleague or a product manager or somebody else who says, no, C++ is too big, it doesn't work for embedded. For those of you who don't, what's your main language of development? C, right? Anybody working with PHP? Okay, one. Yeah. So the interesting thing is that I'm working with IoT these days, and I see a lot of people doing Node.js or JavaScript. I had a colleague presenting earlier this morning about using JavaScript with Node.js style API to program a microcontroller, so working on Zephyr. I'm not going to pass judgment. I think that we follow the engineer's motto here, which is the right tool for the right job. What I'm trying to show you is C++ is a good tool and will do a good job. So I divided my presentation into 3 sections. First, I'm going to convince you that C++ is not bad, that it actually does work for what we want to do in embedded. Then I'm going to show some reasons why it's actually better than the competition, that being C. And then I want to finish with some of the things that are exclusive to C++. I don't have slides for all the things I'm going to say at the end. I'm just going to start rambling about some of the things we started to think about in C++. And I'm going to to answer questions. So feel free to raise your hand if you do not understand me. I understand most of you are not native English speakers, neither am I. So feel free to stop me and ask me something. So as I said, the question we are trying to answer is which is the best language for embedded programming? I already gave you a hint of what the answer is. And I'm not going to say it's C++. The best language is the language you're most comfortable with. I want you to do a good job in developing systems. And especially when we're talking about embedded programming, and we're talking now about the embedded programming connected to the internet, also known as IoT, you need to be doing a good job. These devices need to be updated, need to be securely written, and need to do their jobs without blowing up every 5 days because they just use too much memory. So the correct answer is use the language that you know most, that you are most comfortable with, and serves your job. So PHP might not work on an embedded system. Maybe Java won't work because it is the VM takes too much and garbage collection is not going to help you. But one that might is Go. So you see the little gopher on the top there. It is actually a compiled language, right? I don't know too much about it, but I keep hearing from colleagues who do that this is an awesome language. And more than that, we're here at the Embedded Linux conference. Go, because of the way it is developed, enforces basically that everything has to be open source. But anyway, I digress. Python and Ruby are good options as well. Even though they are interpreted languages, they can be byte compiled. They have a garbage collection, which may not work for everybody. The normal options we have are C and C++. So again, that's what I'm going to be looking into. Let's start with a couple of facts, or myths. C++ is more complex than C. Fact or myth? It's a fact. So it's actually a fact because, yes, the standard is bigger. I'm going to take a parenthesis here and talk about what the languages are. So both C and C++ are developed as part of this International Standards Group, ISO, or organization, ISO. They are both standards in that organization, and if you want to read the specification, you usually go to your national body and you download, you buy, the specification comes in a book. They are quite big. This text is very dense. It's meant to describe an abstract virtual machine that would produce something. Point is, the C++ standard is longer and it is complex because it does more stuff. That doesn't mean the language is more difficult. Another one, C++ language generates more code and or requires more RAM. Myth. That is indeed a myth. The language is designed around you don't pay for what you don't use, right? And even some of the language features can be turned off with certain compiler switches. So we're going to talk about exceptions later. For the moment, if you just want to not pay for the cost of exceptions, you're just writing code that doesn't use exceptions, there's a switch that you can pass to your compiler, will turn them off, and you don't pay for the cost of it. Right? So, which options those are? So if you're not using exceptions, for example, GCC, you're going to use fno exceptions. And this other option that I actually hadn't thought of until I was actually writing the code to figure out the difference in size, the asynchronous unwind tables. And that's interesting because that applies to C as well. I was trying to compare the size of a byte of a certain function you're going to see later in the presentation between using exceptions and using manual error detection and error handling in C. And it turns out that the C compiler, GCC, was producing the equivalent information for unwind. That is, how do you throw an exception through that function? Which would have meant that if you did, that C code would be unsafe because it did not properly handle the case of the exception going through the propagation. So if you want to use C++ without exceptions, those two options. If you, in addition to not using exceptions, you're neither using type ID or dynamic casting, there's an extra option you can use called FNO-RTTI, which stands for runtime type information. That turns off the runtime type information. Most of the time, if you're writing compact C++ code, you're not going to see any difference. That one appears when you, besides these two operators, when you have polymorphic classes with virtual functions. So the moment that you have a virtual function, the compiler will emit the runtime type information for that particular class. So you can save a couple of bytes by not having it. It's going to be about 20, 30 bytes per class. And if you're not using the standard library, and that's going to be a big problem for us to discuss, you can actually disable the use of the standard library. Now, you can't turn completely off, because the compiler will still do a couple of things that are required. So some of the things that the GCC and G++ and Clang do, and any other C++ compiler do, is they call out to a couple of methods, or you use a couple of symbols from the C++ language support. Right? Both GCC and Clang's libraries, I'm going to see later, have sub-libraries that contains those symbols, so you can use only those. And if you install on a regular Linux distribution, those actually come as a static library, so you can easily compile a C++ application that uses nothing more than the C library. Another myth would be the C++ language hides things from the compiler. And I realized that I did not hide everything in my slides. So you know this is supposed to be, what the hell is the rest of it? That was not supposed to happen. So this is what happens when you don't. So I reviewed all my slides, but I never ran them through in presentation mode. So the animations, I never looked into them. So it's a myth. You can hide stuff, yes, but no more than you can do with macros in C. In fact, I would say that the extensiveness of macros, because you can't do many things in C, because there are certain things you cannot do in C that you can in C++, the use of macros in C++ is smaller. In turn, that means the converse means that you're using macros a lot more in C, and that has sometimes a very unexpected effect. So my rule of thumb, whenever you, and this is for you, if you're compiling code and you see an error from the compiler that makes absolutely no sense because it has nothing to do with the code that you're looking at, look at the preprocessor output. It's very often that somebody defined a macro to one of the words that you use in that line, and then the compiler thinks that when you wrote interface, and this happens often, I have a lot of code in dbus that uses the word interface, that word should not appear there. It's not a valid variable name. Of course not, because Windows.h defines it to be struct. So you cannot define something like that. So be careful. We had cases of, let me give you another example. You're writing an application that defines int, sun, and moon. Can anybody tell me which operating system that will not compile on? I'm going to give you a hint. One of the companies is named after that. So now they no longer exist independently, but on Solaris, made by Sun Microsystems, Sun is defined to 1. Trust me, when I compiled the code, there was an example 10 years ago, like, why doesn't this it compile on everybody else, and then it didn't compile on the Solaris compiler. I started to blame the compiler until I figured that one out. So anyway, I digress. The next question, and let's see if the animation works. Using templates is more expensive. So the answer here, I'm going to hedge my bets, and again, the animation didn't work. It's yes and no. So templates by themselves do not imply that you're using more code or more RAM. That's a myth. It does increases the compilation time because the compiler has to do more things, and thus increases the memory usage of the compiler. But by itself, they do not cause more code or more RAM to be used. However, because of the way people currently use templates and the fact that we're trying to produce more optimal code by eliminating function calls, eliminating out of line, all of this ends up as inline code, it does end up increasing the code size. It's not a requirement for templates for that to happen, but it does happen the way that templates are usually used. So both yes and no. And the last one, in the animations again, I'm just going to skip the animation. So C++ compilers are not as good as C compilers. That's a myth. So if you're using any of the major C compilers today, their C++ compilers are equivalently good. So both Clang, GCC, Microsoft's Visual Studio Compiler, the one from Intel, the company I work on, they are just as good in C and C++. In Microsoft's case, the C++ part is even better because they do follow the C++ standard. They do not follow the C standard. So, for example, they only brought C99 support to their compiler when C++ started requiring it. However, they're not as widely supported on embedded platforms. That's why I'm here. So, for example, I was talking to Anas Nashif, from the lead architect in Zephyr, and said, yeah, we don't support C++. Nobody has wanted it to do it. But if you want to give it a try, take a look, and I'll probably be doing that. Just as I mentioned, compilers and standard, and this will give you a picture of what I said before about the libraries. So, on a regular Linux system, you're going to see either of these two compilers, GCC or Clang. They're more or less equivalently good in code generation. In micro benchmarking, I can tell you GCC still generates better code than Clang. Whether that's going to remain for long or not, we don't know. GCC also does have a couple more aggressive optimizations. So we had a problem in Qt recently related to the dead store elimination. I will not get into the details of it. It's just a new switch they added into GCC 6, and we could not see what was wrong in our code. It took a while to identify that, yes, we were violating some of the requirements of the C++ language, and therefore the compiler was right to eliminate some of the code that we did. So both Clang and GCC are equivalently good. GCC comes with its own standard C++ library, and they're not very imaginative with the name. It's called libstandard C++. Clang, because libstandard C++ was taken, just called libc++. It's an LLVM library. The main difference you're going to see in these two is the license. So the GCC one, like GCC itself, is licensed GPL version 3 with the runtime exception, whereas the LLVM code is more often licensed BSD. So on many of embedded systems, because of the provisions of the GPL, for example, you might prefer to use a BSD. I'm not a lawyer, so this is not a legal recommendation. It's something that you and your legal team need to come look into. Clang has been designed to work with both libraries. So it actually does work with both just fine. And I've seen many Linux distributions that default Clang to use libc++, and my answer is don't do that. Don't try to make that choice on behalf of the user. If the user wants to, there's a switch that you can pass to the Clang command line that will switch it from one to the other, but you should default to using what everybody else is using on your system, which is libc standard C++. In theory, GCC should work with libc++. I have actually never tested it. It's something that I should be looking into soon because of what I said about Zephyr. Inside those two libraries, like I said, there are sub-libraries that support the language itself and do not provide the rest of the standard library definition. And those would be libsupport C++ and libc++ ABI. If you take, for example, on macOS, what Apple has done is that most of the applications today are linked to libc++. And what they've done is that they've replaced libsub C++. They've taken it out, and they've made libc++ ABI a separate shared object. So both libraries link to the same core. As a result, you can actually run applications that link to both libraries at the same time. They're compatible among themselves. Now, you can't actually pass structures that you find in one to the other. So for example, standard string, you're not going to be able to pass across the two libraries. But exceptions are going to work. You're going to be able to call new on one and delete on the other, and that just works just fine. And that's also because all of this ABI has been defined it was actually defined during the Itanium processor. Apparently some people at Intel had too much time on their hands and they decided to do a C++ ABI that was published. Today it's still known as the IA64 C++ ABI, but it applies to almost all of the processors you see today. They depend, the normal libraries depend on libc. So if you're going to look at embedded systems, you're going to have to choose your libc. If you're going to microcontroller systems, that gets interesting because you don't have a libc with a C API and a POSIX API. And more importantly, you don't have a pthread one. So many of the things that exist in the current standard C++ 11, 14, and 17, you might not be able to use on very tiny embedded systems. But if you're looking at Linux, this is just how it works. Any questions so far? Okay, so let's look into why I think C++ is good. Let's start with something that bit me when I was working on, so I'm the maintainer of a C library called TinySeaBoard. It's meant to run on Zephyr. I wrote it in C because, well, I just didn't want to have the fight back then, so I just wrote it in C. It was that simple anyway. Just as I was starting with the project, I had not configured my compiler with any special switches. The following code like this compiles, and you can see that in C, it prints a warning. It doesn't cause an error. In C++, it's an error. And if you're compiling, like you're just starting, you compile this file over there and then working on something else, you never realized that this went through with just a warning. Why is that bad? Let's suppose that G is a function that takes int64. This function here passed a 32-bit parameter. So G did not take a -1. It took a uint max. So I've seen many code bases in C where they actually have a couple of W error, so they turn a few warnings into error. Missing prototypes is one of them. Right? So if you're working in C, you probably want to make W error equals implicit function declaration. Never allow your C code to compile like this. In C++, it's not required because it's not required to make this an error because it is already an error. The language requires that it be defined before. There's another reason for that. It's because C++ supports overloads, so it needs to know which of these functions to call. The ability to call without a prototype is legacy in C. It actually is inherited from B, the language that came before C. So if you didn't know your history, yes, before C came B. In B, you did not declare parameters. So that's why in C you just have the parentheses, you never have anything inside. Everything was simply word sized. So that would have worked here. They didn't have the problem with 64-bit. But that said, we say, yeah, that's just legacy from B. This one I find inexcusable. So in C, casting across different pointer types only triggers a warning. Like in C++, that's an error. So the example here is what happens if I pass a short pointer to an int pointer in a function. The C compiler warns, but does not stop. So this is another one that you might want, if you're using C, to make an error of. In C++, it's an error. I simply cannot tell you why this in C is not an error. I just can't think of any reason why anybody would want to implicitly cast from a short pointer to int pointer. The one below is the dropping of const. That one has more of a reason because the original C language did not have const. So it's a bolted on keyword. It appeared shortly before C++ was invented, so C++ actually came with const. Yeah, I mean, at least it's the right type, but if I drop the const, I might be writing to memory I shouldn't be writing, and if this is pointing to read-only memory, my application will crash. So these are really weird for me working from C++ to accept that they are correct in C. Putting it the other way around, if you program in C++, your code is safer because you will not commit to these errors. The compiler will simply not let you. The next one, according to Linus, is a feature. Void pointers. So you are allowed in C to cast from void into any other pointer without a cast. The most common use of this is int car pointer something equals malloc. You do this very often in C. Now what happens is that malloc returns void pointer, which gets automatically cast to car pointer. In C++, that is not allowed, and here's why. So I have now, instead of 2, I have 3 functions. If you look at the bottommost one, it's the short pointer again. So I'm calling from F, I'm calling G, and that is okay, it casts to void. So my short pointer gets to void star. But the G function takes that void star and casts to int star without checking. So I can't stop you from casting. Casting has a place, it has a use. But let's be sure that you do the right thing. In C++, this would have been caught and would have made you think, oh, which one was this supposed to be? By the way, do I really want to do a void star API? If you can't, don't. You would use templates here. But in C++, it is an error. In C, it's neither an error, not even a warning. So, since we talked about casting, I'm just going to plug in the stricter type safety introduces the cast operators. Here for no other reason that they're easier to grep for. So if you need to figure out if you're doing anything wrong, if you need to do an audit of your code to make sure that you're casting right things to the right things, right? You do a grep for static cast, all of these. It's much easier to find these words which cannot be used in variable names, they cannot be repurposed, than to write a regular expression that does casting of types in C. I would actually say it's impossible to write one. The other advantage of having them is that you can't accidentally do more than what you intended. So if you're using const cast, the only thing you can do is drop the CV qualifiers. CV qualifiers, const and volatile. Yes. But if you're doing a static cast, you're not allowed to drop the const. So you can do a couple of things with static cast, but not cross barriers that are unrelated types, and you cannot drop the const cast. So yes, and sometimes you see longer code in C that does a const cast to something intermediate and then does static cast to the destination. Yes, it's long-winded, but I'm explicitly saying what I'm trying to do. I cannot, by mistake, lose the const. I had code base in Qt that was using old-style casts, and we're C++, we call C casts old-style casts. That's actually the GCC warning for it is W old cast. If you do that, you try to compile. I was trying to remove them. It turns out that the code base, because it had been refactored so many times along the way, it simply could not be done. It simply could not get const safety everywhere and get rid of those annoying C casts. Some functions were supposed to modify, called functions that weren't, and then called back into things that were. Anyway, from the beginning, use them. The next topic is just organize your code into classes. So I searched for, this is glib code. You can see it's actually from GIO, it's a GDBus function. I was just searching for an example of something short that called a couple of functions inside. As you can see, this code, I hope that everybody in the back can see it. By the way, the presentation will be available online later, so you can look into the code. What it does is that it does string new, which allocates something. I have no idea why it needs a null. That's my opinion on API design. Why does it need a null there? Then calls string append C. Well, it is a string. Why do I need to repeat myself that it is a string? So the equivalent code that I just wrote for this with the Qt classes with QByteArray, it just calls append. Now, if you're paying attention, there are two things different in the C++ code from the C. One is more or less evident. Something is missing on the C++ code. The free. We're going to get that into later. The other one is not as evident. And this is something that people actually do complain in C++, because they're saying you're hiding stuff. Can anybody see what is different between the two, what I could be hiding? So the answer is, look at the third append, right? It is equivalent to an append C. I actually looked into what this was supposed to be in glib. It's appending a simple character, right? So it is the same append function. And the reason for that is that we're using overloads in C++. In my opinion, which is not shared by many of the C coders, it is actually better to have the overloads here because they do the right thing and I don't have to worry which of these functions are. It behaves the same way. So if I were to change my arguments, I wouldn't have to change the function. In fact, if this were a QString instead of QByteArray, the code probably would compile anyway and just do the right thing with a QString instead of QByteArray, even though it doesn't operate on characters but on QChar, which are Unicode. Right? So since we're talking about overloads, an improved functionality in C++ are overloads. So I just copied this from both the C and the C++ standards. On the right, you can see the C standard from section 712.7.2. So all of chapter 7 in the C standard is the library. On the C++ standard, since the library is so much bigger, it is many, many chapters. Chapter 26, if I'm not mistaken, is the numeric support. Yeah. So it's just showing what we can do with overloads. On the right side, we have fabs, so floating point absolutes, and you have to call fabs f if I want a float-based floating point absolute. In C++, you have fabs float, fabs double, and fabs long double. You might say, well, why do I care? I'll just call fabs on C. Why does it matter that I have an overload? Have you ever done floating point emulated in CPU? Many of you have. And working with doubles is more expensive. So if I can operate on, maybe not this case of fabs, that's actually an easy one, just flip one bit. But on many operations, using float speeds up the code base. So you want to use, if your code is only floats, you want to keep with floats. You don't want to accidentally use double and increase your runtime because you have to do more precision. In C++, we just call fabs. It will call the right one. And it even has an abs one, which works as integers. That allows us to do generic programming. Now, if you ask me, when I'm working with C, the thing that I miss the most, the one thing I would give my castle for if I could just use in C are exactly destructors. So I copied this from the font here slightly smaller. I was just searching the Linux kernel because glib does not do memory, does not check that malloc succeeded. Not going to that. So I'll search into the kernel of an example of malloc failing, kmalloc failing. And it actually did a couple more things after that, right? So it's not actually easy, so that's a good plus for the kernel. They try to avoid doing complex things in functions to avoid exactly this particular problem. I know one particular function that is much worse than this. It is the one that is called whenever a new process starts. It needs to allocate a ton of different things, so it has at least 10 different go-tos. This is a simple one. It has 2 go-tos. So if you're programming in C, very often you will write code like this. Go-to isn't so bad after all. And I'm not passing judgment. Go-to actually serves a purpose. That one is pretty good. So what you're seeing here is you do a kmalloc, and if it failed, I'm going to return enomem. I could have just written here, they just use the same one below. It does a mutex lock, a spin lock, does some work inside, and in the middle of a loop that happens inside, the path variable might be initialized to false, which indicates to null, which indicates a problem, and in that case, it needs to return an error, name too long. And if that's the case, I need to unlock what I had locked and free the memory, the working buffer. So you have to pair the code like this. And if you have more things that might fail in between, you have to do more of these. So the thing I miss the most in C is resource acquisition is initialization. Somebody said, right, that's the full expansion. So I invented here some functions. So a class called pointer holder, specifically for the kernel, that would do the same thing. And then look at, I'd actually have mutex locker, not mutex lock, and spin locker, not spin lock. So I created 2 extra variables on the stack here, automatic variables. And as you can see from the rest of the modification that I've done, I don't need to remember to unlock them. I don't need to remember to free the buffer. Why is that? Because the destructors will run, right? And the destructors will do it for me.
Which could be called hiding.
Which could be called hiding. It is definitely hiding because I don't see it here. But in code bases where you use RAI, resource acquisition is initialization, properly and only it actually produces safer code. So ever since C++ 11 and more so with C++ 14, there's a trend to get people to stop using raw pointers. There are enough in the C++ standard library, there are enough classes in the C++ standard library to hold them and manage them for you, specifically unique pointer and shared pointer, that you almost never need to deal with them directly. That means that you can still leak if you try hard enough, but it makes it more difficult. The biggest problem you have to face with shared pointers are cyclic reference counting loops. So when A depends on B, B depends on C, C depends on A, you might drop all the references, but since they all have a reference to each other, they never get destroyed. On garbage collection systems, the garbage collector actually has to have enough intelligence to do a pass and verify that it came back to the original one without increasing the use count, and then all of these can actually be thrown away. Same problem exists if you're using reference counting.
I was just pointing that out because I held back when you talked about hiding, but actually this is the one main criticism I always hear from C people, because like, hey, there's only a closing bracket. Why does the compiler produce code?
So yeah, so you're right. Some people in C will complain that the closing bracket produces a lot of code. Yes, it does, right? And the worst one is when you get a compiler error in the opening bracket of your class. That's another issue. yes, I've been hiding code, right? But the interesting thing is this actually made it safer. I've got a colleague who's a really good C coder. He doesn't like C++ at all. There's a feature, an extension in GCC that tells it whenever this variable goes out of scope, call this function. So you can actually implement destructor-like functionality with GCC. It's not part of the C standard, but GCC allows you to do this. So he actually started using this in his own code base because it says, yes, it makes it safer. So I'm willing to sacrifice some verbosity, some explicitness, let's not call it verbosity, for the safer code. We're going to come back to this again later when we do exceptions in a couple of slides. I didn't know exactly what to talk about the containers. I was struggling with what to write in this slide. So the C++ standard library has a lot of containers. It is, in my opinion, the single most important thing that the C++ standard library has. IO streams, throw them in the garbage. The containers are good. And more important than that, those containers in both libc++ and in libc++ are written by the same people who wrote your compiler. They know how the compiler works. That means, hopefully, that the container is the most optimized possible that could exist for that particular compiler. And it often is. It's very hard for you to write something that is as generic and as efficient as the C++ standard compiler, standard containers. Now, you can write specialized code that is more efficient, yes, definitely. But to make it generic to work with everything, it's a little difficult. The example I wanted to give, and we can draw it later after the session, is the normal uses of containers. So in a C code base, what kind of container is the most often used? A linked list. Linked lists. So I was grabbing the glib source code and I found they have garray, which is an array, and I started to figure out where is this used? Almost nowhere. They don't use it in their own code base. glist, however, which is a linked list, they use it very often. In the C++ world, the structure, the container that is most often used is a vector, which is an array. And I can prove to you that a vector of the same number of elements of the same size is more efficient in many factors. So it's faster to search, it's faster to iterate over, it has less memory overhead, so by meaning fewer mallocs. It uses fewer cache lines, and because it's sequential, it actually helps, the CPU can help you because it knows you're going to usually progress sequentially. If you're iterating over a linked list, you might be going all over the place in memory. So the cache lines and the CPU cannot help you by prefetching information that you're going to need a couple of instructions down the line, right? The problem with them, two problems actually. One is they're not optimized for code size. Most often C++ library are optimized for performance. This is why a lot of these things are inline. So yes, it's going to produce the fastest possible by having as a counterpart, putting all the code exactly where you used it. So it's not calling outside. Whereas often when we're doing embedded programming, we want to actually have shorter code to fit whatever memory we need. So the question is, if when I mean optimized, do I mean before or after C++ 11? Both, but more so now with C++ 11, move semantics and more. So they are optimized, and the reason again is because all of this ends up in line. The code is all generic and it ends up in line. Compilers today, both GCC and Clang, are not as smart enough to do code analysis after code generation, and they identify that these blocks of code are actually identical. They do it before, usually before they expand to assembly, and they don't realize that it's actually the same after expanding to assembly. So there's room for improving this more, especially if we want to do optimization for size. Just remember one thing, parenthesis, GCC optimizes for size a lot better than Clang does. So if you're doing compilation with OS, you want GCC, not Clang, today. I said there are two problems. The other problem that I personally have with the standard containers is that the error reporting they have, the only error report they have is exceptions. So there have been discussions on the C++ committee and standard mailing lists. Should we have non-exceptional code? Should we support this? The people there came to a compromise. The answer is like this. We believe, we meaning the C++ standard committee, that exceptions are the answer. We should be using exceptions, and therefore we're going to design our containers and our API around exceptions. That said, we're going to make it easy for people who don't want to use exceptions to still use some functionality. So as an example, the upcoming file system API in the C++ standard is expected to have, as return values, standard expected. So it's a container that has a parameter, a template parameter is your return type, but it might be actually disengaged, containing no value, but instead containing an error code. That allows you to query it, are you an error condition, and handle it normally, or if you don't and just try to access the value, it throws the exception at that point. So it is the compromise we've found. So the people who push and say exceptions are good, their argument is, yes, it looks like it increases code size. It looks like it increases code size. But that's because we're actually handling all possible errors and not missing anything. So I did a test. Let's go back to that C group function inside the kernel code. So I just rewrote it now to use, I have the actual complete code for this, so the ... in the middle is, I have it. I spent some time just doing dummy of everything that it called and all these functions around. I just wanted to know the impact of switching from C with the explicit error checking and gotos to using exceptions. So there are basically 2 points in this function where an exception can be thrown. The first of them is this kmalloc. Right? So I didn't change, I made it so kmalloc is not marked no except, so it might throw. I wrote the actual pointer holder class, and the function in between that actually, you can't see here because you wouldn't be able to read it. The function that would have returned the null path, I made it a throw. Or since it's all non-inline, basically did not mark it as no except. Everything else, all the other functions, especially the ones in the kernel that return void, I simply mark them as no except, which means that the source, the compiler is looking at it and say, I have 2 points possible where it's possibly going to throw. One of them is before anything happens. It's actually the beginning of the function. That's this kmalloc here. So it might just throw and doesn't have to do anything. Or in between in that ... there, in which case it needs to destroy 3 objects. The 2 lockers and the pointer holder. Note that I don't have to return enum, because that's actually an exception thrown. I actually also removed the code that did return ename too long, because that's supposedly now an exception. So if the function inside said, well, I can't fit the name that you wanted me to in the buffer that you passed me, I'm going to throw ename too long. Right? So the only return point in this function, the normal return, is this return 0 at the end. It actually means this function did not need to return int. It could just have been void, because it always succeeds or throws. Right? I actually just realized this when talking to you. I could have made this void. I compiled it, and as an exercise, I used the ABI for the Zephyr operating system, which I believe is also what the kernel uses inside itself. It uses basically passing by registers. As a result, the code size grew 16 bytes. And it added the exception table that wasn't needed before. And this is where I found that the no asynchronous unwind tables was important in C as well. Because when I had just compiled it in C and had not noticed it, it did emit an unwind exception table for C. So the difference between the C unwind table that was there and the C++ unwind table with exceptions was 16 bytes only. So 0, 10x, right? 0x, 1, 0. The other thing that changed, and this is actually where the 16 bytes come from, is that the error handling was removed from the main code path. Really. So I'm going to leave you with that. I had, like I said, a couple of more C++ is awesome. I'm just going to quickly go through them. Lambdas, I love lambdas. It's a good thing to use. They can be used in C as well, as this example shows. The range 4, I'm going to leave you with this and ask you to spot the error. There's an error in the C code. Trust me. Unfortunately, we're running out of time, so I will not give you. Sorry?
Declaring the I in the folder?
No, that was my mistake, I guess. Okay. No, the error is something different. Yes. I did not divide by size of. Actually, GCC complains to you and says you're accessing out of bounds. Clang didn't. Whereas the C++ code is much simpler. To close, there's a bunch of goodies that we're doing in C++ 14 and C++ 17. I don't have the time to explain them all. The language is evolving rapidly, where C is not so much. It's all an ISO standard, but interestingly, the standard itself can be found on GitHub. You can compile it because it's text. They only accept pull requests for editorial changes. Everything else needs to go through mailing list discussions, which we're familiar with. So, unfortunately, I ran out of time. Thank you so much for coming. I'm available in the coffee area afterwards. Yes, and use C++.